I'm going to introduce Andy Young from Asperitas. He's the CTO over there. We've been working together for most of the past year on this integrated solution. Andy will walk everybody through, and then I can help answer questions at the end of the session, and feel free to capture me afterwards. Okay, turn it over to Andy.
That's great. Hi, everybody. Thanks, Eric, for that introduction. Pleasure to join you all here today. So Eric's going to drive the slides. So Eric, let's get straight into this with slide 2, with the title slide. Okay, yeah. So as Eric said, this is a collaboration that we've been running for about a year together. Really, this comes through the collaboration work we've had through our companies, but also through OCP. And I think you can see this success story we have here as being a great example of how OCP can bring players together like Asperitas and ITrenew to really do great engineering work together. So it's a really great celebration of that work. Eric, next slide, please. So yeah, so the key drivers for this work really have been to come up with an energy efficient solution for cooling IT, with really some strong prioritization around sustainability. As you may know, there's a bit of talk on the line. Yeah, so Asperitas have a immersion cooling system, which is based on natural convection. And as you may be also aware, that ITrenew have a great route to market to extend the first life of the IT equipment. So CO2 reduction directly and indirectly, e-waste reduction and heat reuse are really the key drivers for this project. We are showing you today some work, great examples of engineering, really on one server in particular, but of course there's a whole range of servers that we're working on together with ITrenew. Next slide, please, Eric. So yes, so the outputs really through OCP have been to have marketplace listings for the Asperitas tank and trolley. You may have seen that on the marketplace, and also the server solutions coming from ITrenew. This really, as I said before, is a great example of how OCP can bring players together in the market, and the contributions that are made really pay back in terms of how we understand what the needs of the market are, not just in terms of the sustainability credentials, but just what the products need to do in order to be functional in the data center context, in terms of not only the sustainability performance, but the power performance, density, safety of operation, maintenance. All these factors really would not be so apparent to us as solution providers did we not have the great forum of OCP to really drill down into the details of that and understand in a very precise way and a very well articulated way to ensure that the solutions that we develop are actually what the industry needs. Eric, next slide, please. In fact, let's switch on to slide number 6, which is really okay. So before we get into the details of the server development work, which is a major part of this presentation, let's just take a look at the overall solution. So here you can see a photograph of the solution, which is at the systems scale. This is the immersion environment. And just a note to say that this is really a system that really relies only on natural convection, so no moving parts, hence aligning with the sustainability targets around low energy. Of course, robustness is promoted by that as well. But as you'll see, the low moving parts is really challenged by the use of the type of server that we're cooling here in order to overcome the flow impedances, the flow resistance of the design for air servers, and the challenges that come from not having pumps to overcome that, and how we use engineering tools to really understand what the performance criteria are, and also what the performance outcomes would be given the choices we have in developing the server. A big part of that is also our partnership with Shell, who provide our immersion cooling. And you just heard from Puneeth at Shell on some of the areas that we work together on in terms of materials compatibility, but also making sure that it has great mechanical properties and thermal properties as well. So that's the overall system. Of course, that's what the server relies on to provide the immersion environment. So let's now focus into the actual server itself, starting from the air-cooled Leopard servers that ITrenew are remarketing. Eric, I love how you've now in sync with me, so you can move the slides automatically. So this is the server as it comes to us. This is the air-cooled 2OU high Leopard servers. You might be familiar with this configuration. It's very similar indeed, and it's the forerunner of the Tioga Pass, designed for air cooling. You can already see that there's quite a lot of equipment in the flow of the air through the server. So this flow impedance, think about this in terms of a immersion cooled environment. So that liquid has to flow through the CPUs and the other heat sources, but also through this equipment that you're seeing here. We also make a decision fairly early on in the project due to the low power of the servers to increase the density, therefore achieving a power density that we know we can achieve with immersion cooling by going from 2OU to 1OU. So we're going to essentially compact, squash this IT into a smaller space, hence increasing this flow impedance. But you'll see how we work through that as we go forwards. So just bear in mind that this is an air-cooled server by design. Equipment is there in series of the major heat sources, and we're densifying this in terms of going from 2OU down to 1U height. Eric, next slide, please. So a closer look at the actual servers themselves. They're fairly straightforward. Air in one side, out and out of the other. Here you can see the fans, which we remove, of course. And you can see the standard heat sinks, which we maintain because we want to carry over as much of the standard designed for air-cooled components as we can. And on the right-hand side, you can see the AVA board, which really has a very dense form factor and layout of M.2 drives to give local memory, non-volatile memory for the servers in place on a PCIe riser. So this actually is one of those layers in the stack that we talked about. And as we go through the other details of the server, you'll see that it's not just that, but other components beneath it that build up that flow impedance near the outlet. So let's take a closer look at the IT components on the next slide. So as I said, it's a fairly low power board. The CPUs are 120 watt. This, of course, is a few generations behind the current products from Intel, because it's obviously extended first life products. But the temperature requirements of this, due to the low case surface area, are still quite challenging to cool. Low power, but low size, low surface area. And so we really do have to pay close attention to the thermal requirements of the CPU. And as we said, we are maintaining the air-cooled heatsink on top of that to minimize the change to the server. So some challenges thermally there, albeit at a low power, but it's still very much part of the focus of our processes. Alongside the CPU on the next slide, you can see that we have BIMs present as well, which needs to be cooled, but also is a bypass route for the liquid to take, should it not want to pass through the fairly high fin density of the central heat sinks over the CPU. So this is one of the technical risks that we have in immersion, to ensure that we have the flow passing over the heat sources in a proportional way to the heat sources. One of the good things about natural convection, of course, is that the heat itself generates through temperature change locally, the flow in the same locality. So it's sort of a self-correcting approach to cooling, but still the fluid does have inertia. It enters the server at a flow rate due to the downwards inertia from the heat exchanger, as you'll see in the later slides. So bypass is really a consideration, not only in air cooling, but in immersion cooling as well. And so we do pay attention to not only the CPUs, but the other components adjacent to that. And the density of the DIMMs is quite low compared to the heat sinks. So that's really a risk factor that we need to consider. As we said earlier on the next slide, you can see the densest region, which is downstream now on the left of the CPUs, these AVA boards. Yeah, super dense, low heat, but really the fluid can't really find a good path through there. We need to cool them, of course, and that happens, as I said before, naturally through the natural convection action. But really, it is a large flow impedance. It's quite difficult on its own, but if you consider that underneath this component, on the following two slides, there were other heat sources which also they sit in the same stack, and together the AVA board, the NIC, as you can see here, and on the next slide, the M.2 SSD, together really do create that dense region. So we'll see how that's represented in the modeling that we do, and we'll see how that flow impedance affects the through flow of the dielectric liquid. Of course, when we go into design, we try and maintain the original configuration of the IT equipment as far as we can. Minimal change means least cost, and you know, if it ain't broke, don't fix it. So engineers like to see if how things work, but having options is the name of the game. Also, so we considered once we placed the servers, as you can see in our standard 1U height cassette, we considered the other locations below the server that we could move those storage devices into. On the left, you can see the power supply, bottom left-hand corner, and locations where we could put 2.5 and 3.5 inch drives if that was needed. And these were alternate layouts that we can use either instead of or in addition to expand the local storage of the server. And just for your information, this is a standard OCP open cassette that you can see this large outline of the container around the servers. So it's an example of how we're using the OCP standard components in terms of the server form factor in our designs. So on the next slide, you can see how that form factor of the cassettes is modeled in CAD. You can see the layout without the additional servers and with the AVA board, the NICs, and you can't see them because they're underneath the AVAs, but the other components in place. Those green components in the stack is the flow impedances that we're talking about. So we do a full model of this in our processes, including the power supply that you can see at the bottom with that little orange square. And we don't model that server independently in terms of the flow because it has to be modeled in the context of the overall module. The module is the tank that we showed in the earlier slides. The reason for that is because we don't only have heat sources and flow impedance at the server scale, but we also have the same on the module scale too. So there's a cooling source which increases density, but also presents flow impedance in parallel to alongside the server. So we model our servers in the module in order to give a full digital twin representation of the server in context of how it is cooled. So on the next slide, you can see some results from this work. Yeah, so on the On the left-hand side, you can see that we modeled the server in 3 dimensions, looking at the flow paths of the dielectric liquid from shell as it moves through the S5X coolant. It looks like a bit of a mess of lines, but what that's showing you is the trajectories that the flow takes. And what we look at very carefully is to make sure that there's no recirculation of the fluid from the hot layers at the top down to the cool layers at the bottom, to make sure that we have a good stratified temperature distribution going through. Each of the servers, the 3 servers which are shown on the screen, are each getting a good flow. And you can see that really on the image on the right. There is an attraction of flow to the heatsink, you can see on the bottom left, and a good attraction on the others too. The central server does seem to not be getting quite as much cooling, but actually when we look at the thermal results, you'll see that each of the servers are cooled adequately well. At the top of the screen of the pictures, you can see the exit flow. So the flow enters on the bottom left, goes through the IT and exits on the top left, and is cooled by the heat exchangers. And that flow is nice, uniform, well organized, and no recirculation. So no mixing of the hot or heated liquid into the lower regions of the cassette. So that's the flow distribution. And we're seeing good distribution. You can see on the left-hand image the bypass that we expected to see from the AVA and other components. But it thankfully doesn't seem to be affecting the flow through the server to a great extent. So on the top images, those flow lines passing over those gray blocks representing the AVA board regions in that stack. Yes, it is causing some bypass, but we're seeing good distribution nonetheless. Moving on to the next slide, you can see the temperature distribution. This shows the stratification of temperature, the colorful banding going from blue to red. Nice, doesn't show any gross mixing, which is diluting the cooling potential of the immersion cooled environment. So good banding means no degradation of the thermal environment. On the right-hand side, we can see the temperatures of the case of the processors, and they are currently with a flow water temperature of 40 degrees. We find we have a 15-degree margin, so 15 degrees overcooling of the CPUs, which implies that we could operate this at a water inlet temperature of 55 degrees. So which is a great outcome from the simulation for warm water cooling for heat reuse. Let's see how that looks from the physical testing.
There's 3
the
minutes
physical
left.
product is shown on the next slide. Eric, great.
Yeah, Andy, you heard that. So we're being politely given the 3-minute mark, just in case you want to improve your flow.
Sure. So this is the physical product as it's built and tested. Moving on to the next slide. The sensors placed are just the standard sensors that we get from the IPMI data from the server, as you can see referred here. On the next slide, you can see the air benchmarking that we do before we do immersion cooling to give us a reference point for performance. And on the next slide, you can see the comparison between the air-cooled benchmark and the immersion performance assessment. So here we have maintenance of the frequency of the processors. It's not affected, albeit slightly, but we attribute that to the sampling error of the frequency rate measurement. And we see great stability of the temperature and good performance in terms of temperature of the CPUs. On the next slide, the bar charts show comparison between the air-cooled and the immersion-cooled results. So great comparison, great results in terms of frequency. And the immersion cooling performance is showing good temperatures relative to the air-cooled. The references are the CPU 0 and 1 position switches because the server is inverted in immersion. But the main point here is that we have 41-degree warm water inlet temperature performance achieved. Slightly lower, or actually 10 degrees plus lower than that predicted from the simulation, but there were some compromises on the build regarding heat sinks, which we're working on together with ITrenew. So it's a good indication of performance, and we believe we can close the gap between measurements and the full potential from the CFD results by optimizing the heatsink, which was indeed designed for air cooling. We can make improvements for that heatsink by looking how it can be optimized for immersion. So all in all, a great outcome. We are working also on a big basin solution based on the same immersion, natural convection approach to cooling. So more news to follow on big basin and other servers. But in summary, really a great outcome for us and great working with ITrenew, and great to have this collaboration, which has really been enabled by our membership in OCP and the way that we work together. Thank you so much. Eric, thank you for being a great slide operator and partner on this project, and I look forward to your questions.
Yeah, so I'm afraid there's not much time for questions. Maybe one question from the audience still.
Anybody brave?
Right, and otherwise, be happy to refer to Eric. Thank you indeed for operating the slides. And thank you very much, Andy, for hosting this presentation remotely. We're up for a break, and we're going to continue in this room in 10 minutes from now. Hope to see you all back.